and we think we understand how it works in the solar wind and in galaxy formation and in the atmosphere of stars. But maybe we haven't got it all right down to the last decimal point, and maybe we have to go back to the laboratory and look at the real thing, create some ball lightning, try our best to create these situations and replicate what we see.
Okay, yeah. And how about, stuff like regular lightning? This is plasma too, correct?
Well, regular lightning, oh sure. Somebody once said, whether it was Tony Peratt or Hannes Alfvén or Irving Langmuir, he's another one we haven't discussed.
Yeah.
Another Nobel winner. I'm sorry, I lost my train of thought.
Regarding regular lightning, yeah.
Sure. The only place that plasma isn't important is on the surfaces of the rocky planets like Mercury and Earth and Mars. But it's important everywhere else, and the aurora certainly is an example of a plasma. And as you mentioned, lightning.
Yeah.
Lightning is very definitely plasma, and it's an electrical discharge down through the oxygen and nitrogen atmosphere of Earth, ionizing those atoms. And what lightning is a plasma in the so-called arc mode of operation. There are three modes of operation of plasma. One is called the dark mode, one is called the normal glow mode, and one is arc.
Okay.
The examples would be very quickly, the dark mode is the ionosphere of Earth. It doesn't normally glow. You can't see it. It does make some radio noise, but it's normally not visible, so people ignore it. And then, of course, the glow mode is the average neon sign, eat at Joe's, here it is, that's plasma inside there.
Okay, yeah.
In the glow mode. And then the arc mode is, as you mentioned, lightning, or that spark that jumps between your finger and the doorknob on a very dry winter day.
Yeah.
And of course, the electric arc welding machine, that's plasma in the arc mode as well. The thing that distinguishes the arc mode is that it also generates ultraviolet, and if humans look at it, their eyes suffer.
Yeah. So, I mean, what is plasma? Is it really a strong electrical field, or what is it?
Well, plasma essentially, this is a total oversimplification, and people who know better are probably going to yell at me for saying this, but just to get your hand around it, plasma is essentially ionized gas. If you take gas and put it in a tube and put an electrode at one end and an electrode at the other, and raise one of those electrodes to a higher voltage than the other, so you've got an anode and a cathode, and you get current flowing through there, you will essentially rip off some of the electrons from the outer valence orbits on those atoms.
Yeah.
And so you've liberated electrons inside there, and so the electrons have a negative charge, and the remaining rest of the atom, the neutrons and protons and remaining electrons, have an equal but opposite positive charge. And so they will then, in a gas, in a tube like that, they'll begin to move, and they'll respond to those electrical anodes. And those forces are tremendously strong. So, and I might say, too, that plasma is also the electrons that are in a copper wire that, say, run to your coffee maker. That's also a plasma, a free-flowing sea of charge. And the idea, this is sort of an interesting, I think, an analogy, is that you don't have to put your coffee pot at a lower point than the electrical outlet in the wall in order to get the electrons to run downhill into the coffee pot. The electrons in a wire pay absolutely no attention to gravity whatsoever.
I see.
That's exactly the difference between plasma cosmology and the standard cosmology, which says gravity is the only thing that's working out there. Well, if it is plasma, and we think it is, plasma doesn't pay any attention to gravity for the simple reason that the electric forces are, as I said, 10 to the 39th power stronger than gravity. So it's not that gravity isn't out there. It's just that it's completely overpowered by the Maxwell and Lorentz forces.
Oh, okay, yeah, interesting. And as we were speaking of different forms of lightning, I know that there is another, I don't know if we should call it type or whatever, but that actually goes upward. I think that these are referred to as spirits or something like that, right?
Oh, you're talking about the elves and the sprites?
Sprites, that's right.
Sprites,
Yeah.
Sure. It's exactly the same as lightning, but it's just in a different form. The plasma is in a different shape. The altitude, of course, above, way up in the atmosphere, the pressure is much less, and so the plasma takes on a different shape. The sprites look sort of like the tentacles of like an octopus hanging down.
Yeah, and these are huge, right?
More of a blue torus, like a donut shape.
Yeah.
Thing, yeah. And
these are huge, right?
Absolutely, yeah. And they are certainly electrical in nature. And the idea of the sun's, the solar wind, so-called, that's really a solar plasma being connected down through by, let's say, the same mechanism that creates the aurora down into Earth. There is a definite transfer of electricity between the sun, the solar wind, down into Earth, and whether it's all via just plain old thunderstorms that we're all familiar with, or whether it's by some other means of getting that electric charge down. Do you have dust devils in Sweden? Do you know what I mean by a dust devil?
Yeah, I do. I know what you mean. We have them very, very seldomly here, but I know what you mean.
If a farmer's plowing his field and he creates some dust, once in a while you'll see that thing swirl up and it looks like a tornado or a twister or the kind of water spout that you'd see over the ocean.
Yeah.
And those they did some. I happened to be present here in the Arizona desert when the University of Arizona and my old institute, University of Massachusetts, did some research on these dust devils. The reason they were doing it is because they knew that on the surface of Mars there are tremendous dust devils, ones that dwarf anything here on Earth, and they wanted to know why, what makes them, what are their properties, and they discovered that there were some very strange electrical effects happening right underneath those and up in the core of them. So there are all sorts of electrical paths from the way upper atmosphere down to the surface of Earth.
Interesting. So is this some kind of cosmological discharge going on here, or why is this happening? I mean,
well, yes, nothing magical. I mean, it's if there's a difference in accumulated charge, if you get a bunch of negative charges over here and a bunch of positive charges over there, they're going to want to come together.
Yeah, sure.
Current, there'll be a drift, and
it's
just in figuring out why they got separated and where they are and what they're going to do. And not a lot of people have been studying this sort of thing.
Yeah.
But as I say, it's just plain old hard science. There's nothing magical about it.
Yeah, exactly.
But you do have to study it, otherwise you're going to be amazed by it and say, "Gee whiz, what is that? That's strange."
Yeah, absolutely. I read somewhere that the Earth actually is negatively charged. Is this correct?
Well, it depends. When you say negatively charged, you always have to say with respect to what. Kind of like saying, the analogy I give is what is the velocity of this fly, this little insect flying around inside the cabin of a jet aircraft at 37,000 feet? And the answer is, well, it's either 500 miles an hour with respect to the Earth's surface, or it's 1 mile an hour with respect to the seats in the cabin.
Yeah.
So you can say, well, Earth is at a positive voltage with respect to Saturn? Probably so.
Ah.
It's probably at a negative voltage with respect to the Sun, as far as we can tell.
Yeah.
So one thing is sure. Everybody, most people who've had any, even high school level physics, will realize that all the objects in creation have mass. There's a certain you weigh a certain amount, I weigh a certain amount, the teacup weighs a certain amount, there's a certain mass in every object.
Mm.
It's also true that those objects have a certain charge. And you say, well, gee, how do you measure that? Well, the object will take on from its environment whatever charge it needs in order to reduce the voltage between it and what it's touching to zero.
Ah. Mm.
So in other words, you and I and everyone sitting here on the surface of the Earth are grounded.
Yeah.
In Britain, I don't know what the phrase is in Sweden, but in Britain you say, well, you're connected to main Earth, which is the voltage of Earth.
Yeah.
Now, if you take off in a spaceship or even in an airplane, and you break that connection, that conductive connection between you and the Earth,
Yeah.
you will take on whatever charge you have to take on, such that there is no, or approximately no, voltage difference between you and the medium through which you're flying, i.e. the upper atmosphere or whatever.
Ah, okay.
If it's a space probe that's on its way to Pluto, it will take on whatever charge it needs to take on, such that it reduces the voltage between it and the solar plasma that's right around it to zero. And that's the problem is that's why we can't measure the voltage of what is the voltage of the solar wind out somewhere near Jupiter, say.
Yeah, yeah.
Because we can't get out there to measure it without taking on the same voltage.
Yeah.
So if you hang a voltmeter lead out the side of your spaceship out there, it's going to read zero. That might be very, very different from the voltage that was on that space probe while it was sitting on the surface of Earth. But in the process, along the trip, you've accumulated charge on this thing, on this probe, such that there is no difference between it and out there. But it certainly will take on charge.
Very interesting. And couldn't we kind of connect this with when, I guess foreign to our solar system, at least foreign comets come into our system? Because I've seen a few of the SOHO images that photograph the sun, of course, that it seems to me some instances look like there is a discharge between comets and the sun. Have you?
Oh, absolutely, yeah. Well, I think one of the best pieces of evidence that the Alfvén and Birkeland and Langmuir and all the rest of the fathers of plasma cosmology were correct aren't comets. If you and my friend Wal Thornhill, who you mentioned earlier, made a fantastic prediction that proved to be correct in regard to this a couple of years ago. I think it was in 2004, perhaps 2005. NASA decided to throw a block of copper at an incoming comet. Remember that?
Yeah, sure.
It was called Deep Impact.
Yeah.
And, well, Thornhill thought about that, and he said, before they do that, he said, I'm going to make a prediction. If I'm right, and, of course, all of the people in our group said, yes, you're right, Wal. If the comet is an electrically charged body, which everything in the solar system is charged to some degree or other, and the reason we don't care particularly is that planets, at least as far as we know, stay pretty much where they're supposed to stay, but comets don't. Comets spend a long time way, way out beyond Pluto, and then all of a sudden come flashing in around the sun very, very rapidly, and then go back out and hang out there in the deep space for another 50 years or whatever. Well, as they come in very rapidly, they are trying to equalize their voltage with respect to the solar plasma, but they're traveling so rapidly that there is a voltage difference between them and the plasma right near them. And if they come in fast enough and quick enough into a high enough voltage region, they begin to show a plasma discharge, which is their tail. And also, and I think you alluded to it, they also have been seen to throw out